Thanks. Hello everyone. My name is Pablo. A little bit more about myself. I used to be a principal research scientist at Censam up to late 2015. I used to work with the Michael Trentrafilou, Nick Patrikalakis, and George Barbastatis groups. And I joined the SUTD. I'm now part of the faculty at the Engineering and Product Development pillar, along with Roland. So today I'm going to talk about some of the work that I've been doing in my group since I left Censam. Let me start first with a short caveat. While most of the talks in this workshop have been very close to the field of environment and environmental studies, my work in soft robotics, of course, it'll start closely, I guess, aligned with the environment. But for most of the talk, I will deviate a little bit from the topic, but I'll try to converge again towards the environment towards the end of the talk, and I hope it's entertaining for most of you. Okay, so having said that, let me just start by motivating what I'm going to talk about for the rest of my time. And it's related to the idea of monitoring the environment, right? And I guess this doesn't come to a surprise to most of you after hearing the talks yesterday and today. The environment and pollution are a very complex system, right? There's a mix of chemical, biological, fluid mechanics phenomena, and measurements are key to understand these systems, right? Unfortunately, the hardware that is available to us at the moment to gather these measurements is not ideal, right? We can do better. And primarily the hardware that we have available to us lacks adaptability and robustness. Anybody that has worked in field studies can attest that right now it's inconceivable to leave a sensor unattended in the ocean for more than a week, especially here in Southeast Asia, that the ocean is so rich in life. Biofouling is a big problem, right? When you leave buoys in the coast, if you come back after a week, you're going to see a little microcosm growing next to your hardware, and you have to maintain, you have to baby the hardware to be able to have it working. So it's inconceivable to leave something on its own for a couple of months, a year, and more than that, right? So that was a big inspiration to develop tools to achieve that. So our objectives were to use advanced robotics tools to enable this long-term exploration and monitoring of the environment, and in more generally speaking, unstructured environments. And if we can do this, there are a couple of interesting ideas that we could explore. And let me give you one example. And I'm going to motivate this with an analogy to fluid mechanics. When you're trying to understand fluid dynamics phenomena, in this case, for example, vorticity, and I'm showing here data, the velocity vector field that we somehow captured in an experiment. If we look at the data, the velocity vector field that is in an Eulerian reference frame, right? This is the reference frame of the lab. We can sort of see that there is some rotation going on, but we cannot really see the boundary of the vortex. We cannot do any further quantitative analysis about the momentum of the vortex. It's where it doesn't help us that much. Now, if we look at the same data from a different reference frame, a Lagrangian reference frame, that means a reference frame moving with the dynamics of the flow, we can more clearly see the dynamics that are there, the vortex, right? We can clearly see the boundary, therefore we can do some calculations about the momentum that this vortex is carrying, and we can essentially understand better what's going on, right? So that's the motivation, ideally. If we can have a way to have measurements that track the interesting dynamics in the environment for long enough, we can reveal some interesting phenomena that might be present there. But to do that, we need to, of course, develop devices that are capable of being there in the environment, measuring things for extended periods of time. So my objectives were to track, of course, and reveal the environment dynamics using robotic markers. And to do that, we need to exploit various aspects of robotics: agility, robustness, awareness. The general idea was to have this fleet of soft robots that were acting more or less like plankton, right? That were basically being carried around by the environment dynamics and performing measurements while deployed, and measuring interesting things such as temperature, salinity, dissolved oxygen, nutrients, etc. And of course, it shouldn't come as a surprise, given the title of my talk, that I am offering the thought that soft robots are a good way of accomplishing this. Well, some of the soft robots, why is that? Because some of the soft robots we're developing provide a very robust base for vehicles that can be deployed for long periods of time. Some of the soft sensors that we can fabricate give us feedback that currently sensors cannot provide, and this is some work that I started back when I was working with Michael. Also, some of the flexibility that is afforded to us with soft robots open up new locomotion capabilities, and especially in unsteady locomotion using large flexible fins as propulsors. So what are soft robots? Perhaps not everyone here is aware of this field, so let me give you a short introductory slide. These are some examples of soft robots. The main difference between soft robotics and traditional robotics are the materials. Whereas traditional robots are assemblies of discrete, stiff components where a lot of metals, composites, hard plastics are used. Soft robots primarily use polymers, hydrogels, very soft, squishy materials. These are some examples of my work at MIT. This is a walker developed by the Whitesides group at Harvard. This is the Octobot at Harvard too. This is a tentacle manipulator by Daniela Ross's group at CSAIL. This is a soft gripper by iRobot, soft sensor by Carnegie Mellon, an example of a hand, robotic hand. You can think of soft robots as composite structures, right? So the materials that you use play a key role on the performance of the robot, whether it is locomotion, grasping, manipulation, sensing, etc. Another interesting feature, so I have a movie here. I have a movie here that I want to show you guys, but I'm not sure if it's going to be able to play. I hope your laptop doesn't crash on me. Anyways, let's see if it plays now. If not, I'll just skip it. Well, another interesting byproduct of soft robots is the materials we use, polymers, hydrogens, and polymers we primarily are using now, silicons, are relatively impervious to biofouling. We've done some studies with DSO, for example, where we place some samples of these materials for long periods of time, for a month almost, in marine environments here in Singapore, and you can see very little biofouling has accumulated. We put, I don't have the pictures now, but next to these samples we put regular metallic components, and of course after a week these are unrecognizable. Okay, so this is where the talk starts deviating a little bit from the environment. So I mentioned that we're proposing soft robots as an interesting new tool in advanced robotics to do useful environmental studies. The performance of soft robots is very closely related to the materials we use, basically how we fabricate them, right? So how do we fabricate currently soft robots? So I'm calling this making robust hardware 1.0. Currently, the fabrication of soft robots relies primarily on casting, right? We find the distributions of these polymers that we need in the body to achieve locomotion, sensing, etc. And we make molds and we cast the components required. This usually happens in various types of setups. We cast different components in different machines. Then we aggregate, we assemble the robots. So the resolutions tend to be low. Multiple steps are involved. The geometries that we can achieve are fairly limited. It basically depends on how good we are at producing molds. The materials that we currently use, again, these polymers, hydrogels, in general have limited or no functionality. They primarily provide structural properties. Additive manufacturing, AM, provides multi-material printing possibilities. Maybe you are familiar with the Stratasys, the PolyJet printers from Stratasys that can print various materials ranging from things that feel like thermoplastics to some materials that feel more rubber-like. Unfortunately, these materials are UV-based polymers, which means that these materials remain sensitive to UV for the rest of their life, so you cannot really deploy them in the field, especially here that we have so much UV in the environment. They will degrade. They provide very low strains. They break at around 50% strain. Most soft robots see strains upwards of 100%. So there's some challenges. So what my group has been doing is trying to develop new fabrication approaches to enable adaptive and functional features to soft robot bodies, and we're calling this making robots hardware 2.0. And we're doing this, or we're trying to do this by essentially developing tools that allow us to do direct fabrication of multi-material soft composites, right? With steps that will allow us to carefully tailor the material properties, and I'm talking about, broadly speaking, material properties: viscoelasticity, density, chemistry, biology, electrical properties, magnetic properties, etc. All these using materials that are still capable of large deformations and are also resilient to the environment and to UV. And the functionality that we want to endow these soft composites involves basically adaptability. We want to have devices that can show large, fast, and reversible material property changes, and as well as morphological changes. And I'm giving you some examples here of the types of robots that we're currently building, right? They have embedded sensors, embedded actuators. They can morph. So some of the ideas we're exploring are inspired by a cartoon, an old cartoon that I used to watch when I was a kid. This is actually older. This is from the 60s. It's called Milton the Monster. We got it back in the 80s in South America, where I'm from. And it's essentially, it presents a very interesting fabrication approach, right? This is a mad scientist that makes monsters, but you can think of them as robots, right? Automata. And you can see that essentially using a lot of chemistry, right? He has a mold, he puts some chemicals, and boom, voila, you have an automata, in this case, Milton. He made the mistake of putting too much a potion for the heart, so he's a rather caring monster. So it's a fun cartoon. 50 years after this cartoon, we actually have the technology to do this. And it's coming, for the most part, from bioprinting. We have various tools that allow us to direct deposit and direct print various materials. For the most part, these technologies have been focusing on materials that can support living cells. This is to test tissue scaffolds, to test drugs, etc. Unfortunately, most of the materials that are used in these approaches are not compatible with oil-based materials, with silicon. That's the bedrock of soft robotics. So my group is working on trying to adapt some of these tools to be used with silicon. And our concept is, in a nutshell, presented in this slide, right? So when we want to build a particular robot, we use FDM, which is a type of 3D printing, to print a mold. In this case, let's call this little container the mold. We print it, we fabricate it in place. In the same machine, we deposit a matrix material that's going to be the foundation of the body. We fill this mold with a material. And then using various dispensers, we proceed to embed different features inside this body using different patterns, right? And these inks that we use to embed patterns can have various types of material properties, right? And they can be isotropic, anisotropic, and can have other interesting properties as well. And the idea is to end up with anisotropic material distributions and bodies that are essentially soft composites, right? And these are some of the examples of the types of composites that we can fabricate. We can also combine multiple matrix materials once a given layer has cured. So this is, in general, the concept. Let me give you an example, actually, of how we apply this to build one of the stingrays, the little stingrays. So this is the the setup where we 3D print first the mold for the Stingray using FDM. We place some internal components. We then deposit the matrix material for the body, and then we embed some features. In this case, we embed features inside the fin to allow us to tailor the kinematics of the fin so that we can improve swimming performance. So this is the machine. These are as an example of one of the machines we're using. We're essentially hacking commercial 3D printers. We're adding a bunch of dispensers. We have XYZ positioning with a heated plate. We have hot filament extruders to 3D print using various thermoplastics. We also have cold extruders to 3D print clays and plasticines. And we also have a variety of high precision pressure control dispensers that allow us to print with these various inks, right? We can also do subtractive manufacturing with a mill head and a laser. So the bottom line, these are cheap. These are affordable. You don't need to spend $500,000 in a machine to fabricate this. I have to show you this quickly. You might think, well, what's the big deal? Cake makers have been doing this for years, right? Like happy birthday on top of your cake. Well, actually, the fluid mechanics is a little bit more complex than that, right? We're embedding a highly viscous ink inside a highly viscous body. Why viscosity? Because once we write or we embed something inside, we want that feature to remain in place, right? So viscosity plays a big role. Of course, as we print, we don't want any crevices created by the dispenser, by the needle of the dispenser. We don't want any crevices to remain there, right? So we have to take various considerations on the fluid mechanics and also functionalize both the materials for the matrix and the inks. In a nutshell, I'm going to try to summarize this. We're using non-Newtonian. We need to make both the matrix and the inks non-Newtonian, shear thinning, so that while no stress is applied to them, they remain in place because of the viscosity. But when we apply some shear stress on them, for example, when we are depositing them, the viscosity is low enough that we can extrude them easily, right? So these are some examples of the types of features that we can embed 3D print. And at the moment, we're not too concerned with the resolution. The smallest thickness of features that we can print are in the order of 100 microns. The spacing between the features are also of the same ballpark. We can make very sharp turns, so we can print 90 degrees without a problem. These are some examples of the arrays. We can functionalize to the inks to display luminosity. And I'm writing SUTD in one of those samples. So we have gotten very good at doing this. We can also print self-intersecting paths. We, of course, want to characterize the various performance we can achieve with these composites, right? Whether it's mechanical, chemical, biological. This is an example of the mechanical tests we are developing based on this ASTM standard to characterize the composites that we can create. And we developed simple models, again, to also try to estimate, in this case, the material properties of the composites that we print and compare them with experiments. I'm going to skip through this because I think I don't have that much time left. In terms of design, there's many interesting things that we can do as well. Once we have a target kinematics in the case of locomotion that we need to achieve, right? Or for sensing, it can be a type of sensitivity, or for actuation, it might be a stress generation, etc. We essentially do an inverse problem, and we try to we solve for the material distribution that is needed to give us that performance. Right? Now we have the problem of what is the best way to achieve this material distribution, given that we can print almost anything inside the body, right? How do we optimize the geometries that we use? How do we optimize the density of the material that we use? The material combinations, printing speed, materials usage, etc. All these we're exploring. And let me give you, I'm going to finish giving you a couple of examples. This is how we use this approach to functionalize the bodies of the stingrays. We essentially print these composite features on the fin to tailor the fin kinematics And we do this because this allows us to control the thrust generation. And the movies here show various stingrays with and without the features embedded. And if we plot the amplitude envelope of the kinematics, we can see that the composites actually make a difference in tailoring the kinematics, and the resulting thrusts are noticeable. The resulting changes in thrust are noticeable, I should say. So that's for agility for locomotion. We use this also to make sensors. The whiskers that we continue to work in collaboration with Michael's group, we're making soft follicles. In this case, the ink now is a combination of platinum catalyzed silicon with silver. So it's a conductive ink. So by changing the geometry, we can essentially have features that are resistive. The resistance change given the stress applied to it. So we can measure normal tangential stresses, and we use this on the follicles of the whiskers that we're developing to put in our soft robots. And this movie just shows how the resistance change when we're applying a stress. Finally, more in line with the environment, nutrients are a big deal. Sandri just mentioned, right? The abundance of nutrients is one of the indicators of the onset of algal blooms. One of the inks we're developing also uses ionogel-based gels to detect nitrates. And we're using this Grace reaction, right? And in a nutshell, the way it works is the gels are doped with two ions that react with nitrate in the environment, and that when the reaction takes place, there's a production of an ink that allows us to visually identify the presence of nitrate. So let me finish just by listing, of course, this work is ongoing. We're working on various areas on manufacturing. In terms of deploying this in the real world, of course, we're doing more work on control. Roland mentioned that we're going to start a collaboration soon where we're combining swarming with some of our hardware. Power is an issue too. We're working on printing batteries, soft batteries inside the bodies of the robots. Computation as well, soft computation. And I should mention, we're still developing inks. We're actually developing an ink that is a type of hyperelastic bone. It has the same flexural rigidity and porosity of bone. So let me acknowledge my funding and thank my team. And that's all for me. Thank you.
So maybe we have time for one question while the next speaker is setting up. I have a question actually. So you mentioned that the soft robots could go up to order of 10 meters in scale. What are actually the largest soft robots there, and are there issues in terms of scaling the amount of skeleton versus as you increase in size?
No, I didn't talk about the scale. So when you talk about the scales, there's various considerations. One is, can you fabricate that large of a soft robot? And also, what is say you're talking about locomotion, right? Is the locomotion that you're trying to fabricate going to be useful at that scale, right? So the robots that I showed they swim using large fin deformations, right? So they essentially the type of locomotion that works well at high Reynolds numbers. Right? The largest one that we have built of that type of robot is a Stingray, and it has a diameter in the order of 1 meter. The smallest one we built is a couple of inches.
Thanks.